Hello everyone. Today we are going to discuss the next topic of Module 2, that is MOSFET internal capacitances and higher frequency model. So before to this we have studied three topics, that is regarding the MOSFET configurations, that is common source, common gate and common drain, and then we have seen the derivations of various characterizing parameters of common source amplifier without source resistance, then common source amplifier with source resistance, and then we have seen the source follower or common drain configuration and the characterizing parameters of source followers. So, and then we have got to know like what are all the characterizing parameters of these three different configurations. Today we are going to see one of the a very important topic, that is regarding the internal capacitance of the MOSFET. Okay, so for whatever the circuits we have seen, that is the device models such as small signal models, whichever we have seen, these circuits or models does not contain any capacitances. Of course, we know whenever we consider the practical cases, that is capacitances are included. So for whatever the models we have seen, we have just predicted that which is going to give the constant gains, and it is of independent of the frequency. But when I include the capacitances, the circuit depends upon the frequency. At that time what happens, your gain, it does not remain constant, and we know gain of every MOSFET amplifiers, it falls off at some frequencies. So it depends upon the frequencies. The gain, it is going to fall at some frequencies. Similarly, when I take an example of a digital logic inverter using the MOSFET, which exhibits a finite non-zero propagation delay. Okay, so to be able to predict these results, the MOSFET model must be augmented by including the internal capacitances. Today we are going to see what happens when we include the internal capacitances in the MOSFET, and what are the different types of capacitances we can see in the MOSFET. Okay, so basically, yeah. So similar to your BJT, your MOSFET has also got the internal capacitances. So these internal capacitances, or I can say stray capacitance or parasitic capacitance, is unavoidable and typically unwanted that exists between the parts of an electronic component or the circuit simply because of how close they are to one another. So what is capacitance actually? Capacitance is nothing but it is the ability of a system to store an electric charge. So here the gate material in the MOSFET is isolated from the other terminals by an oxide film. That is the thing we know already now. That is a gate terminal. It is being isolated from the other terminals. Other terminals means source, drain and body. So it is isolated from these terminals by an oxide film. So the silicon under the gate has the opposite polarity to the drain and the source, which results in the formation of the PN junctions between the gate drain and between the gate drain and the source regions. So whatever here we are going to get, that is CGS, drain, gate, source and gate drain. CGS and CGD are the capacitances of the oxide layer. You can see here this oxide layer which isolates gate, drain and gate source. Okay, so whatever the capacitances we can see here, this is considered as gate source, and here this is nothing but gate drain. So CGS and CGD are the capacitances of the oxide layers, while CDS, there is one more capacitances, that is between the drain and the source, is determined by the junction capacitances of the internal diodes. So we are going to see this in detail. That is, basically there are two types of internal capacitances in the MOSFET. One is called gate capacitance, gate capacitive effect, and then next is the source body and drain body depletion layer capacitances, or we call it as the junction capacitances. So let us see what is this gate capacitance now. So the gate electrode, we know this gate electrode, see this is a gate electrode. Gate electrode, which is nothing but a polysilicon, forms a parallel plate capacitor with the channel. So what is channel here? That is the region under the gate. That is a gate. It is, this is nothing but an electrode, and after that there will be a oxide layer, and below the oxide layer we will be having a channel. That is nothing but the N-type channel, induced N-type channel. So this gate electrode forms a parallel plate capacitor with the channel with the oxide layer serving as a capacitor dielectric. So this oxide layer which will be acting as a dielectric of a capacitor. So one end of the capacitor will be having the gate electrode, and the other end of the capacitor will be having the channel. And in between this channel and the gate electrode, we are having a oxide layer which is acting as a dielectric. So it is denoted its value per unit area as COX. C subscript small x OX, which represents it is a oxide layer capacitance. It is called gate capacitance. Next is the next capacitance, that is source body or drain body depletion layer capacitance, or it is known as the junction capacitances. These capacitances, it is occurring because of the PN junctions. So these are the capacitances of the reversed biased PN junctions formed by the N plus region. See what is N plus region here? N plus regions are nothing but which is taken as the source and the drain. Okay, source and the drain, and here the body which is nothing but we are taking this as a p-type substrate, right? So source and drain, it is nothing but the N plus, and this is placed under the p-type substrate. So here it forms a reverse bias PN junction. So whatever the capacitances of the reverse bias PN junction formed by the N plus source region and the p-type substrate, it is called as the source diffusion. And p-type substrate and N plus drain region and the p-type substrate, it is nothing but the drain diffusion. Okay, source diffusion, drain diffusions. Because of this, whatever the capacitances we are going to obtain, it is called junction capacitances. So altogether, because of the gate capacitance, gate capacitive effect, we will be having three capacitances, that is CGS, CGD, and with respect to body, that is CGB. And the junction capacitance is two junction capacitances, that is CSB and CDB. Okay, CSB and CDB. So these two capacitive effects can be modeled by including the capacitances in the MOSFET model between its four terminals. Four terminals means that is gain, source, drain, and body. There will be 5 capacitances in total, that is 3 because of the first effect, gate capacitive effect, and 2 because of the junction capacitive effect. So because of gate capacitive effect, we will be getting the capacitances as CGS, CGD, CGB, that is gate source, gate drain, gate body. And then 2 capacitances CSB, that is source body and drain body. This is because of the drain junction capacitance. So where the subscript indicate, whatever the subscript here, CG, GS, GD, GB, SB and DB, it indicate the location of the capacitance in the model. That is, capacitances occurs between the gate and the source. Here gate and drain, gate and body, source body, drain body. Okay, and this picture which gives a clear picture, that is capacitances between the gate and the drain here, gate and the source here, and between the gate and the body it is not shown, between the source and the body, between the drain and the body. So altogether we can classify the capacitances as like this: 3 capacitances: input capacitance, output capacitance, and feedback capacitance. Input capacitances are nothing but CGS and the CGD, gate source, gate drain. And the output capacitances, CGD, it will come gate drain and drain source, okay. And then the feedback capacitance is nothing but CGD. Next, let us see in detail. So the gate capacitance effect. So the gate capacitive effect can be modeled by three capacitances we know, that is the capacitance because of gate source, between gate drain and gate body. The values of these capacitances can be determined as follows. We know the MOSFET, it is going to operate in three different regions, that is in cutoff region, saturation region and the triode region. And in the triode region, MOSFET operates in the triode region at very small VDS, drain to source voltage will be very much small in the triode region. So the channel will be uniform in depth. That is, whatever the channel formed below the gate layer, that is channel formed between the source and the drain, the width of this channel will be uniform. And the depth of this, not width, depth of the channel will be uniform because we are providing the very small VDS. So the MOSFET enters into the triode region. So the gate channel capacitances will be, what might be the gate channel capacitances? It is width of the channel, length of the channel into the capacitance, that is COX, and can be modeled by dividing it equally between the source and the drain ends. So two different ends are there. We are going to equally divide this to source and drain ends. Thus, the capacitance value will become, that is CGS, which is equals to CGD and which is equals to W into L into COX divided by 2, because it has been equally divided between source and the drain ends. So this is obviously an approximation, but as we discussed in the previous model, this is obviously an approximation, but works well for the triode region operation even when VDS is not small also. Okay. So this is regarding the triode region. Now let us go for the saturation region. When the MOSFET operates in saturation region, what is VDS? The channel has tapered. In a sense, the channel, there is a pinch of, the channel has tapered shape and is pinched off at or near the drain end. There is a pinch off near the drain end. So what happens there? CGD, that is the capacitance because of between the gate and the drain, this will become 0 because there is a pinch off effect over there near the drain. So CGD will be 0. So what happens to CGS, that is the source end, is your capacitance, it will become 2/3 of WLCOX. So it can be shown that gate to channel capacitance in this case is approximately 2/3 times WL, width, length, COX, and can be modeled by assigning this entire amount to CGS and 0 amount to CGD because the channel is pinched off at the drain end. So this is the capacitances values at the saturation region. Next, the last region, that is a cutoff region. When the MOSFET is under cutoff region, the channel disappears. We know the channel disappears. Thus, what is the value? CGS and CGD will be 0. So there comes the picture of your CGB, that is capacitance between the gate and the body. So the whatever the value, that is WLCOX, it is nothing but your now gate to body capacitance, capacitance between the gate and the body. Yes. So we can model the gate capacitive effect by assigning the capacitance, that is WLCOX, to the gate body model capacitance. So yes, and so under the triode region, the CGS CGD will be equal. It is equally divided between the source and the drain capacitance. So the value is WLCOX divided by 2, and then here the value, that is CGS, that is MOSFET under the saturation. Your CGD is 0 because of the pinch of channel is pinched off at the drain, and then CGS will be 2/3 of WLCOX. And whenever the MOSFET under cutoff region, your channel disappears, so CGS CGD value will be 0. So there comes the picture of gate body model capacitance, that is CGB, which is equals to WLCOX. Now one more capacitance is there, that is out of this CGS, CGB and CGS, CGD and CGB, that is called overlap capacitance. So what is this overlap capacitance? That is a small capacitive component that should be added to CGS and CGD in all the preceding formulas. This is the capacitance that results from the fact that source and drain diffusions extend slightly under the gate oxide. So if overlap length is denoted LOV, we see that the overlap capacitance component is, that is COE, overlap capacitance, which is equals to W into L, that is overlap length is denoted as LOV into COX. So typically this length, overlap length, is nothing but it will range from 0.05 to 0.1 L, that is the length of the channel. And next come that is related to the gate capacitance effect, gate capacitive effect, and the next is junction capacitance. So junction capacitance, two capacitances, CSB and CDB. CSB is source body, drain body. Okay, so the depletion layer capacitances of two reverse bias PN junctions formed between each of the source and drain diffusions and the body can be determined using the formula. There is a formula to determine this. Thus, for the source diffusion, we have source body capacitance, that is CSB. See, this particular CSB formula we derived from this particular capacitance equation, that is CJ. Junction capacitance value can be calculated like this, that is Cj naught divided by root of 1 plus Vr by V naught, where Vr is nothing but the applied reverse voltage and V naught is nothing but the barrier voltage or built-in voltage. And what is the Cg naught and CJ, the capacitance that relates the change in the charge Q to a change in the voltage. Okay, so V naught is nothing but the barrier voltage or built-in voltage. Similar to this, the equation for source body capacitance is written over here, that is J is replaced by source body SB. Okay, J naught is replaced by SB naught, and VR, that is a reverse voltage, is replaced by the source body voltage divided by V naught is nothing but the junction built-in voltage. Okay, so CSB naught divided by root of 1 plus VSB by V naught. Of course, the derivation for this is not given directly. The formula it has been given. You need to remember this formula. CSB is equals to CSB naught divided by root of 1 plus VSB by V naught. Okay, so where CSB naught is a value of CSB, that is source body capacitance at 0 body source bias, that is VSB as 0. Is the magnitude, VSB is the magnitude of the reverse bias voltage, and V naught is the junction built-in voltage, which will be the value of V naught will be 0.6 volt to 0.8 volt usually. So similarly for the drain diffusion, we have the drain body capacitance, that is here this is the source body capacitance. One more is drain body capacitance. Similar to this, you have the formula CdB naught divided by root of 1 plus VdB divided by V naught. Okay, similar to that. So where dB naught is the capacitance value at 0 reverse voltage, and VdB is the magnitude of this reverse bias voltage. So we have assumed that for both the junctions the grading coefficient. It should be noted also that each of these junction capacitances include a component arising from bottom side of the diffusion and a component arising from the side walls of the diffusion. So altogether we will be considering diffusion has 3 wall side walls that are in contact with the substrate and thus contribute to the junction capacitances. Okay, so junction capacitances, two formulas, CSB and CDB. So that is nothing but the internal capacitances of the MOSFET. So whatever we have studied now, internal capacitances, which includes basically two types of internal capacitance, gate capacitance and the junction capacitance. So altogether 5 capacitances are there. CGS, between capacitance between gate source, capacitance between gate drain, and capacitance between gate body, and then capacitance between the source body, and capacitance between the drain body. So these three capacitances, CGS, CGB and CGD, because of the gate capacitance effect, and CSB and CDP because of the source body drain body depletion layer capacitance. Okay, this is because of source diffusion, this is because of the drain diffusions. And we can classify this capacitances as three different types: input capacitance, output capacitance and feedback capacitance. Input capacitance is nothing but CGS plus CGD. Okay, and output capacitance is CDS and CGD, and CGD will be considered as feedback capacitance. So CGD, which will be common for all the types of capacitance, input, output, feedback. Next is gate capacitive effect, that is your MOSFET, it enters into three different regions: cutoff region, saturation and triode region. So in the triode region, your VDS, it will be very much small, so channel will be formed and which is of the uniform depth. So your CGS, it will be equals to CGD because the capacitance, it will be divided equally between the source and the drain. So it will be like formula is W into L COX divided by 2. If the MOSFET is in saturation region, what happens here? The channel, it is going to be pinched off at the drain side. So CGD will be 0. So the entire amount of the capacitance, it is nothing but CGS. So it is 2 by 3 times WLCOX in the saturation region. And in the cutoff region, what happens? Your channel, it is disappears. So CGS and CGD will be 0, and CGB, here it forms CGB, that is capacitance between the gate and the body. So it will be equals to W into L into COX. And here also comes one more capacitance, that is the overlap capacitance. It is denoted as COV, which is equals to W into LOV. What is this LOV? LO is nothing but the overlap length, which is denoted as LOV. And this typical value of this LOV is 0.05 to 0.1 L. Okay, that into COX. And next is the junction capacitance. Two capacitances, then one is because of the source diffusion and one more is because of the drain diffusion. Source diffusion, it is CSB, and the formula is CSB naught divided by root of 1 plus VSB by V naught. VSB is nothing but the magnitude of the reverse bias voltage, and V naught is nothing but the barrier voltage or built-in voltage, and the value of this is 0.6 volt to 0.8 volt. And next is the CDB, which is nothing but CDV naught divided by root of 1 plus VDB divided by V naught, where VDB is the magnitude of the reverse bias voltage and V naught is the barrier voltage, that is 0.6 volt to 0.8 volt range, typical range. And VDB, CDB naught is nothing but the capacitance value at 0 reverse bias voltage. Okay, so that completes the internal capacitance. So the next class we shall see the problem under this internal capacitance and the high frequency model, and thereby we are going to complete this particular MOSFET high frequency model and the internal capacitance of the MOSFET chapter. Okay, so today let us summarize, let us quickly go through all the amplifier type and the characteristic of these amplifier types. So we know the characterizing parameters are nothing but the input resistance, open circuit voltage gain, and then the output resistance, and then the voltage gain, overall voltage gain. It is denoted as either AB or GB. So one of the amplifier type we have seen, it is common source without source resistance RS. So when there is without source resistance, there is a change in your open circuit voltage gain and the overall gain. That is, we need to include one factor 1 plus GM into RS in the with the source. Okay, only that is the difference. So R in input resistance, it will be infinite. It will be a very large value. So ideally it is infinite. And then the open circuit voltage, we have derived this equation. So it is minus GM into RD. GM is the transconductance and RD is the drain resistance. and R naught output resistance, it is equals to RD. And then overall voltage gain. See, in the open circuit voltage gain, we need not include the load resistance, but in the overall voltage gain, we need to include RL. This RL will be connected in parallel with RD. So the equation to calculate AV, overall voltage gain, AV or GV, it is minus GM RD parallel to RL. And when we come to common resistance with the common source with source resistance, Rin is infinite. Open circuit voltage gain, it is reduced by the factor 1 plus Gm into Rs. So you compare these two equations, open circuit voltage gain, how it differs? It differs by this factor, that is 1 plus Gm into Rs. So your common source with Rs, the gain is reduced by the factor 1 plus Gm into Rs. And then the output resistance remains the same, that is RD, but your overall voltage gain, again it is been reduced by the factor 1 plus Gm into Rs. So you need to remember only this factor in common source with Rs, that is the gain reducing factor 1 plus Gm into Rs. This also can be written as RD parallel RL, that is Gm taking that to the denominator, 1 plus Gm plus Rs. Either you remember 1 plus Gm Rs or else 1 by Gm plus Rs. I think this will be easy for you to remember, 1 plus Gm into Rs. And the last configuration we have seen, it is the source follower. It is a source follower. So the input resistance of the source follower, it will be infinite. And the source follower, we know always the source open circuit voltage gain, it will be 1. It will be 1. So source follower find applications where the input resistance or input impedance we require high and output resistance as low. Not for the gain purpose, we will be making use of source follower. Okay, so the output resistance, it is 1 over Gm, it is not equals to Rd, it is 1 over Gm, and AV, it is RL divided by RL plus 1 over Gm. So how we will be obtaining the gain as 1 is, that is by considering RL as load resistance as infinite. If this is infinite, infinite by infinite is nothing but 1. So AV, the formula you need to remember, RL divided by RL plus 1 over Gm. Overall voltage gain, and output resistance is 1 by Gm. Open circuit voltage gain is 1. So this is the summary of your amplifier type and various characteristic parameters of these three amplifier types, that is common source with Rs, and source follower. So next class we shall discuss the problem under the gate capacitance, under the MOSFET internal capacitance, and the last topic is the small topic, that is frequency model, high frequency model of the MOSFET, and thereby we are going to complete this particular chapter. Thank you. See you in the next session.